Welcome to solverfy.
Okay, in this problem we have electrons being accelerated in a voltage, a potential difference of 0.1 kiloelectron volts, passing through a thin slit and creating an interference pattern on a screen some far distance away. And we know that the first minimum appears at about plus or minus 14.6 degrees from the central maximum. We're first asked in part one to consider whether these electrons will be relativistic or not. And in part B, we're asked to find the slit width. So the equations we'll need, in order to figure out if the electrons are relativistic, we need to find its kinetic energy, which will allow us to obtain its velocity. And we can tell, based on if it's a significant fraction of the speed of light, whether relativistic effects will be important. We also will need the classic equation for single slit interference, A sine theta equals n lambda, where A is the slit width, theta is the degree, the angle to various minimas, n determines is the number index for the minima, and lambda is the wavelength of the light, or in this case, particles. We will also need to use the equation to obtain the wavelength of our particles, which is h over p, and can also be expressed as h over mv. And that should be everything we need. So let's jump into it. So for the first part, because the electrons are being accelerated by a potential difference, we can simply say that the kinetic energy will be equal to the potential energy change, which is E, the charge, times the voltage difference, K equals EV. And note, this is not electron volts, this is actually the electron charge E times a voltage V. We can then can set this equal to 1/2 mv squared, definition of kinetic energy. And we can solve for the velocity, which will give us root 2 electron volts voltage, not electron volts, electron charge times voltage over the mass. Plugging in some numbers, recall the electron charge, 1.6 e to the negative 19 coulombs. The voltage we're given is 0.1 kilovolts, which is simply 100 volts, all over the electron charge of 9.1, or the electron mass, 9.1 e, negative 31 kilograms. And this will give us a velocity of 5.93 10 to the 6. So comparing this to the speed of light, which is 3 times 10 to the 8, you can see that this is a very, very small fraction of the speed of light. Thus, relativistic effects should not appear in an appreciable way, and so we can justify using non-relativistic expressions. So onward to part B. We're given the angle for the first minimum, which means that A sine 14.6 degrees is equal to 1 times lambda. N for the first minimum would be 1. Thus, we can solve for the slit width. A equals lambda over A, or lambda over sine 14.6 degrees. And all that's left is we need to replace lambda with an expression involving velocities and masses. So using our formula, lambda equals h over mv, we can replace our lambda with this equivalent expression, and we have h over mv sine 14.6 degrees. And when we plug in our velocity and our mass and Planck's constant, we will end up with a slit width of 4.8796 times 10 to the negative 10 meters, which is 0.488 nanometers. And when all the numbers are plugged in, you will see that this wavelength, or this length of the slit width, will be about 4 times the wavelength of the electron. Just an interesting fact. So that's it